Okay, hello. Welcome to chapter 14 of the syllabus 9478, right? The topic on electric fields, right? So we'll cover all these learning objectives, right? Sorry, it's hanging. Yeah, okay, so it works, all right? So anyway, we'll move on. We'll cover all these objectives. You should recognize these formulas as being quite similar to your gravitational field chapter formulas, right? I'll try and bring about the similarities and differences as I go about the chapter. Right, let's start with first learning objective, uh, knowing Coulomb's law. So your job as spelled out here in the learning objectives in the syllabus is to recall and use Coulomb's law in the form F equal 1 over 4 pi epsilon naught, right? So this thing over here is called epsilon naught, Q1, Q2 over R squared for electric force between 2 point charges in free space or air, right? So this epsilon naught is for free space or air, right? And this formula I just want you to pay attention is only valid for force between 2 point charges, all right? So this formula is a special case, right? Coulomb's law states that the electric force acting between 2 point charges, Q1 and Q2, right, is directly proportional to the product of their charges and inversely proportional to the square of the separation between the charges, right? The direction of the force is along the line joining the 2 point charges. So F is proportional to Q1, Q2 over R squared. That's what Coulomb's law say, right? We know that proportional can be replaced by equal to K, Q1, Q2 over R squared. But the K in this case is 1 over 4 pi epsilon naught, right? So this is the constant, right? So we'll just write it as F equal Q1, Q2 divided by 4 pi epsilon naught R squared, right? So this is the formula that you will be using most often. Epsilon naught is a number given to you in the data sheet. You do not have to memorize this number, all right? This is a time, sorry. Oops. Yeah, sorry, I'll correct this later, but there's a times here, all right? Times, okay. Sorry about this is a times, right? So anyway, yeah, well, yeah, it's a time. I'll fix it later. Right. So anyway, I just remind you that this is only valid for 2 point charges. Right. So you should draw 2 point charges whenever you can to apply this formula. Just to know it's between 2 point charges. Right. Do note that this is only applicable to point charges. What is point charges? It means the charge exists at a point only. Right. But for practical purposes, charge bodies can be treated as point charges if they are separated far apart, such that the size of each of the charge body is negligible to the separation, right? So what this means is that normally for spheres, they are not actually point charges because point charge is really one dot, right? So this is a point charge okay, for example, it's really one dot. But if I look at a sphere has a radius r, right? For example, this r and this also r. You can call this r2, doesn't matter, right? R1 and R2, right? However, if the distance between the two spheres are actually much greater, small r is much greater than R1 or R2, then we can assume this is a point charge, and therefore we can use this formula over here, right? That's what it's trying to say, okay? So example, 2 point charges, Q1 plus 2 charge, plus 2 Coulomb, and small q, uh, plus 1 Coulomb are separated by a distance of 3 meters, right? So can you find the A and B first? Try to do A and B. Magnitude and direction of the force of Q on small q, right? Right, I hope you have paused and tried the question. Okay, so I think the first step you want to do is actually try and figure out whether or not this is a repulsive or attractive force. All right, I will remind you that this one of the things different about this as opposed to gravitation. Gravitation, there's only mass, right? So when there's only mass, the formula for gravitational force is just G m1 m2 over r squared, right? But for charges and for gravitation, right, it's always attractive because there's only one mass. But for charges, there are two types of charge. There's the positive charge and the negative charge. So you have to figure out whether the charges are actually repelling or attracting, right? This one you should have learned in IP3 or IP4 or Sec 3 or Sec 4, correct? So if you look at the forces first, they are both positive, right? Therefore, they must be repelling, right? They look something like that, right? So what's the magnitude and direction of the force of capital Q on small q? That means I'm looking for this force. Sorry. Yeah, I'm looking for this force, right? Because this is small q. Right? So I just apply the Coulomb's formula, law formula, right? 1 over 4 pi epsilon naught q over r square. I substitute everything inside, I get this force, right? So this is the size of this force, and the direction is away from capital Q, right? So this is away from capital Q, right? If I look at small q on big Q to answer B, I know that this is actually action-reaction pair because they are Newton's third law pairs. Right? Otherwise, or if you don't know that, never mind also. In this case, you can just substitute all the numbers again to get the exact same value of 2.0 times 10 to the power minus 3 newtons. Right? But of course, in this case, it's away from small q. Right? Then you can try C yourself. Pause and try C. Okay, we're back from the pause. I hope you have taken the time to pause and try part C. So if Q is negatively charged with twice its original magnitude, determine the new magnitude and direction. Right, again, we should try and draw some diagram like that to get a sense of the direction of the forces. Since now one is positive and one is negative, it's attractive lah. Right, so the diagram should look something like that. Right, and I want to find this force. Right, then you can substitute into, again, Coulomb's law equation, and you should get some number like that. Right, here, whether or not you substitute the Q as positive or negative, in my opinion, not so important because normally this is done in tandem with a diagram, right? So the direction is actually normally shown in the diagram, right? So I won't bother too much with the negative or positive sign here, but the story changes when we do the scalar part, right? So that means we do energy and potential later, not potential, yeah, correct. Energy and potential later, you realize substituting the negative and positive is important, right? But if you want to always be consistent, then you substitute negative and positive everywhere lah. Doesn't matter lah. Just know that this sign here doesn't really say a lot lah. Okay, right? So if you want the direction, you should actually draw the diagram to figure it out, right? So magnitude of the force is 4.0 and is actually towards capital Q, right? Because positive, negative must attract. Right, we move on to the next chapter on electric fields. Right, this should be again studied at the year 3 or year 4. Right, so field of a force is a region of space within which there could be non-contact force acting on the object placed in the field. Right, specifically, electric field is a space within which there's an electric force acting on a charged object placed in the field. Okay, remembering that we have two types of charged object, could be positive and negative. Right, that will be significant a little bit later. Right, the electric field at a point in an electric field strength at a point in an electric field is defined as the electric force per unit positive charge exerted on a small test charge placed at the point, right? So mathematically, the electric field strength at a point can be expressed as E divided by F over small q. Okay, so this is a general formula. It can be used in any case. Okay, again, I remind you that above this one can only be used for 2-point charges, right? This formula is specialized to 2-point charges. This one is a general formula. E equal F over Q can be used for general things. That means everything you can use this formula. You don't have to worry about what is the context. All right, so yeah, the units are given here. I'm not going to talk about them. Electric field strength is a vector, you should know that. Right, the direction of electric field strength at a point in the electric field is the same as that of the force acting on small positive test charge, small q placed at that point, right? Because you should realize the direction of electric field strength is defined as the force acting on a small positive test charge. Alright, moving on to the LO, right? So the next part of the LO requires us to know E equal 1 over 4 pi epsilon naught Q over R squared is the electric field strength due to a point charge, right? So this formula is only applicable to a point charge, so don't anyhow apply to, for example, parallel plates, okay? This formula is only for point charge. Right, so moving on, how do we acquire this formula? It's not difficult if you think about it. It's very similar to gravitation. You have a small positive test charge at a distance r from a point charge q. By Coulomb's law, the small charge will experience 1 over 4 pi epsilon naught q over r square. From definition of electric field, E equal F over Q, right? You take this divided by Q, the Q will cancel away, right? Like that. Then what you're left with is the electric field is Q over 4 pi epsilon naught r squared, right? Do note that the direction of this electric field depends on the charge causing the electric field, right? So if the charge is positive, all right, then the field direction is outwards from the charge. So if this positive charge, the field direction is outwards, right? And if this charge is negative, the field direction is inwards, all right? Yeah, so if Q is positive, right, then the field exerted by Q on this point, a distance r away, is given by the formula Q over 4 pi epsilon naught r squared, where r is this distance, and the direction is outwards from Q if Q is a positive charge, right, in accordance with this, right, and if Q is negative charge, then the same formula applies for the strength of the field, but the direction of Q is actually towards, the direction of electric field is actually towards the charge, if this is a negative charge, right, so just note that this will be a negative charge, and this will be a positive charge. Right, so if you have more than one electric field vector at a point, what you should do to find the resultant vector is to vector sum them, right? This is expected, right? So electric field lines are used to help us visualize electric fields. Electric field line is an imaginary line or curves drawn through a region of space so that its tangent at any point is in the direction of the electric field vector at that point. All right, I'll explain this with a diagram later on, so don't worry too much about it. All right, again, these are all very basic stuff you should know already. Direction of the field is a tangent to the field at each point. It's the direction of the force a small stationary positive dash charge will experience if it is placed at that point, right? Spacing between the lines indicates strength of the field. Stronger field will have more closely spaced lines, right? So if we look at this diagram, this is stronger field, this is weaker field, right? Because the spacing between here is bigger than this one. Right, electric field lines are either originate on positive charges or come in from infinity, either terminate on negative charges or extend out to infinity. The number of lines originating from a positive charge or terminating on negative charge must be proportional to the magnitude of the charge, right? They do not intersect, right? Field lines cannot intersect one, right? So just take note of that. In a uniform field, the strength is the same at all points, and therefore they are represented by parallel lines equally spaced as shown below, right? The field is stronger if the lines are closer together. So this one is closer together, so it's stronger field. In a non-uniform field, the lines are drawn such that the tangent to the field at a point gives the direction of the electric field strength at a point as shown, right? So if this is the electric field lines, these curves here, right, and I want the electric field at P, I need to draw a tangent at P, all right, and then the direction of the electric field at point P, right, follows the direction of the arrow of this field line. Okay, so likewise, if I want the field strength here, all right, I should draw a tangent like that. All right, and the question is, should the arrow size here be bigger or smaller than this arrow over here? Right, then we have to look at the spacing. This spacing is a lot closer, at least it's somewhat closer than this one. So this should be weaker. So this one, the field line should be smaller size, right? So the length of this arrow should be smaller than this arrow, okay, because this distance is bigger than this distance. Okay, so this shows weaker field in this direction. Okay, field lines touch the surface of conductors at 90 degrees. Right, the reason for this, you can read the appendix. Right, appendix is for, it's not technically in syllabus, but if you are a stronger student, I think reading appendix will help you gain a better appreciation of what's going on. Right, electric field line pattern, as we talked about before, positive charge is outwards, negative charge producing field line is inwards. Right, closeness is related to strength, this one we talked about, right? Isolated sphere, basically this is a point charge, right, and this is a sphere, right? So in a positively charged spherical conductor that's isolated, right, the charges inside will spread out uniformly. All right, and the electric field at every point within the conductor itself is zero. So if I ask you what's the electric field strength at the conductor inside this sphere, which is positive charge and isolated from other charges, right? The electric field strength inside is zero, right? Because if it's not zero, right, then the charge will be still moving. Okay, so the resultant field only acts outside the conductor and is perpendicular to the surface of the conductor. And outside the conductor, the electric field strength is equivalent to that of a point charge with its excess charge located at the center. So from the outside here, right, when we look at the field, right, we cannot tell that this is a spherical conductor, right, or a point charge, right? To us, looking from here, right, there's no difference between the two. Because if it is for a positive point charge, I will see the exact same lines. Okay, right, so this is an example that I think demonstrates that idea well, right? I'm not going to ask you to do this lah, because I think this one, if you never done before, you won't know how to do, right? So I'll just give you a solution to this, right? We've already discussed this, so you can copy the solution, all right? And we'll come back in the next lesson to carry on.